Hello and welcome to this demo of SigmaTech software version 3.1. In this demo, we're going to showcase the capabilities of SigmaTech software using a real-life example from an organization. The problem statement at that organization is as follows. There was a condensation process which the scientists at the organization were trying to perform using three reactants. Let's say for this example, we call them as X1, X2, and X3. And the scientists were trying to achieve the maximum yield using these three reactants going through the condensation process. The scientists were finding it difficult to finalize the exact quantities of the reactants to be used to achieve the output desired, maximum output desired. The yield of the desired product obtained was very low, but at about 40% against an expected 60%. The experimental trials conducted with the conventional method to improve the yield could not achieve the expected result, expected yield. And they were finding it difficult to find out the variables controlling the yield and in what quantities, and hence it could not be implemented. Since nothing substantial information could be gathered with this rational method of experimentation, again the experimentation was conducted using statistically planned approach using the SigmaTech software, and a maximum of 60% yield was obtained by the simulation of the process model using the SigmaTech software. In addition, the parameters for a robust process, which resulted 57% yield, were also found using simulation and graphical methods with the help of SigmaTech software. We are now going to showcase use the SigmaTech software using this real-life example. At this point, we're going to launch the SigmaTech software. And walk you through the steps of how to use this software for this problem statement. So when you first launch the software, there's a user authentication process. So we log in using user ID and password. After you log in, the initial screen, as you can see on the right hand corner, upper right hand corner, there's a menu bar with three options: File, Admin, Help. Click on the file. We're going to create a new project, and the new project has two options: screening and optimization. For our example, we're going to choose the optimization process. And as I stated earlier, since we are dealing with three variables, three reactants, we'll choose the three variable option under optimization. When you click the three variable option, the next window which the software opens is for the project details to be typed in. Let's call the project name as pyrimidine, and the next input we need to provide to the software is how many responses are we dealing with. Response is nothing but in this case we're trying to achieve the maximum yield. In some cases we also talk about maximum yield and minimize impurities, in which case the responses is 2, but in this case we are only maximizing the yield, so we will call the number of responses as 1. And the next field, we're going to just call the response name as yield itself. Let's call it yield, and we're going to save this project. Now that the project is saved, we're going to go to the next step, pressing next. here you have a again a window where we will input the 3 reactant variable data. First we have to just give a name to these variables. Let's call them M1. Units, let's say just a number, and a low value and high value. So what is the lowest value for each of these variables, within which the process will yield the process will give the desired output. But again, we don't know the right quantity of this reactants which will produce the maximum yield. All we know is the boundary values for these reactants, and that we are going to use as our input for this process in this software. Next to, let us call the variable as M2. Again, the units is number. Type the low and the high values which we know. Let's call X3 as M3. And type the low and high values for the third reactant as well. Now that we have provided the input for these 3 reactants, the low and high value to the software, we're going to save this information. And once it is confirmed, it is saved, we're going to now generate a plan. What the plan gives is a number of experiments to be conducted with a certain proportion of these variables. So it has generated a plan of 8 experiments, the software. And if you see the first experiment you conduct using the lowest values for these 3 reactants which we gave input earlier. The second experiment, we are going to use the highest value for variable x1, the reactant x1, and keep x2, x3 at the lower end. Similarly, if you take experiment number 7, it says x2, x3 you need to keep at the highest value and keep x1 at the lowest value. So on and so forth. Now we conduct the experiments, and after having conducted experiments, we have got the results, and we're going to now capture the results into this software. So the first one, the yield is 52.30. Second one is 50.78, 51.764, 56.275, 0.258, 48.173, 7.089. The final experiment, 51.002. So after having captured the yield output using these 8 experiments, we're going to now save this data, and once it is confirmed that these changes have been saved, the next step is we're going to replicate another set of experiments using the midpoint of these reactant values which was provided earlier, and we're going to repeat that. and that is the reason we call it replicate, and we're going to replicate 4 times. So if you see, it spits out another 4 experiments to be conducted. 9, 10, 11, 12 is midpoints, and we conduct this experiment again and capture the yield output into the software. So when we conducted, the yield output result for the first one is 52.508. Next is 52.90. 2.80. Next 52 point. After having done that, we're going to save this. So now we have a set of 12 experiments which we have conducted using the data which we earlier was provided to the software for each of the reactants, lower and higher value. And we have captured the results, and now we're going to analyze these results. So if you see, there's a button here for us to choose analysis, and the moment you click analysis, the window of statistical analysis appears. Here it can be seen that there's a last column which we call it as SS ratio. Actually, this column denotes the relative contribution of variables and interactions on the yield. The highest positive contribution, as you can see, is for B12, implying that to increase the yield, it requires to increase the reactant X1 and X2 simultaneously. Similarly, B3 is also highest contributing, but negatively, which is inferred by the sign of coefficient. Therefore, to improve the yield, it requires to reduce the level of X3. Now, let's click on the graph and see what happens. So here you can see the graph we have generated in a 3D, and we will now analyze. Now we'll click on the SS ratio, which actually now generates pie chart. And in this pie chart, as you can see, clearly shows B12 and B3 control the process. So the biggest pieces in the pie, as you can see, is B12 and B3, which contribute to the yield. That is one inference you can derive. Further, the nature of the relationship between yield and the input reactants X1, X2, X3, as you can see in the statistical analysis, it says non-linear, indicated in red in this example. Hence, to increase X1, X2 levels and reduce the X3 level, we will now go with composite designs. So now we're going to click on composite, and as you can see, when you click on composite, the software is now asking you, it's giving a plan for us to conduct another 6 experiments, and let's do that and capture the data for that. So when we conduct those 6 additional experiments, which the software is now suggesting us to perform, after conducting them, we are now going to capture the results for the same. For the first, which is the 13th one, is 50.6 396, the next 52.786, which is 55.424, 7.654, 56.617, finally 49.41. Now we're going to save this data, and after having saved this additional plant data, let's now again analyze once more. So when we perform analysis, now you can see the coefficients of the quadratic model are displayed. So basically we know which combination of reactants, and we get an idea of their contribution in translated in the form of a coefficient. Now we are going to use these coefficients and create a simulation, and we're going to now click on simulation, and this throws out two options, systematic and random. We're going to do the systematic simulation and say OK. And in this case we would like to maximize our response, so we're going to choose the maximize option, and it again throws out the 25 simulated runs and their corresponding yields. So you can see that the last two simulations we are able to achieve little over 60% yield. So now let's go and try this in a graphical mode. Let's quickly rotate that, and here what we are doing, since x3 is, we know its contribution is negative, so we are taking the lowest value of x3 and fixing that for the purposes of this experimentation, and we'll analyze x1 and x2. And as you can see, we have taken x1 on the x-axis and x2 on the y-axis. And if you see for x1, after 1.023, pretty much the yield is slowly constant, and it's from 1.023 to 1.091, the yield is now constant, which is at 57.2678. This indicates with this range of x1 value, x3 we know that it has to be lowest, we are able to get a constant output at 57.2678. Yeah. So this indicates that we now know the robust parameters within which we should operate. So we have a robust process for us to conduct this experiment. Also, the last two lines, if you see, they intersect at 60% yield, but that's just at one single point, indicating that at that point we do achieve the desired 60% or little over 60% yield, but since it's just one single point, the process may not be stable at that for those parameters. But if you see the third line, we just showed that it is constant at 57% for x1 from 1.023 to 1.091, indicating that for those values the process is robust. In fact, it can be seen that the yield is 57 to 60 at x1 equal to 1.023 and 1.091, and x2 1.74 to 2.18, and x3 of course is always at 1.0195. Thus, the maximization of the process is established on verification of predicted results, and this is also called design space as required by quality by design principles. This can be seen in a contour diagram as well. Let's go back, and we're going to click on contour. And see how it looks in contour diagrams. So for the contour diagram, we're going to input the yield, the desired yield percentage range. We know it's 57 to 60%. So this yield is achievable for x1 at 1.023 to 1.091 and x2 at 1.74 to 2.18 and x3 at 1.019, which is constant because x3 is the lowest we're going to keep as its contribution is negative. So this actually tells us basically the design space for this process. So if you see the green area, that we can consistently get output from 59 to 60%, which is our design space, and it's a robust process design as we have a range of values for x1, x2, x3, x1, x2, keeping x3 at lowest. This concludes our demo of SigmaTech 3.1 software. Hope you could understand the demo, and if you have any further questions, please reach out to SigmaTech Consultancy and we'll be more than happy to answer your queries. Thank you.